The kernel is the core of your operating system. It's the first thing that loads when your computer starts and the last thing to shut down. Every time you open an app, click save or connect to Wi-Fi, the kernel is quietly doing the heavy lifting behind the scenes. It's the reason your apps don't crash each other, the reason your system can multitask, and the reason a tiny bug can bring everything crashing down with a blue screen. And yet, most people, even developers, rarely think about it. So today, let's break down what the kernel really is, how it works, and why should engineers care so much about it, even in a world of AI, GPUs, and quantum computing. Let's get started. The kernel is the central program in any operating system. Think of it as the brain or command center, sitting right between your software and your hardware. When an app wants to read a file, allocate memory, or talk to your GPU, it doesn't go directly to the hardware. It asks the kernel to do it. That's because apps run in what's called user mode, where they have limited access for safety. The kernel runs in privileged mode, where it has full control over the CPU, memory, and devices. Without the kernel, your system would not know how to schedule apps, protect memory, or talk to a keyboard, SSD, or graphics card. It's invisible to most users, but absolutely critical for everything your computer does. The kernel does 4 big jobs, all happening quietly beneath the surface. It decides which programs run, in what order, and for how long, like a traffic cop directing cars at a busy intersection. When you open Chrome, then Spotify, and then VS Code, the kernel schedules tiny time slices on the CPU for each. This constant juggling is what lets you multitask. The kernel allocates memory to programs and makes sure they don't step on each other's toes. Each app gets its own memory space, so if one misbehaves, like trying to access memory it shouldn't, the kernel blocks it instantly. That's what causes those segmentation fault errors in C. For example, writing to a null or invalid pointer causes the kernel to step in and stop the program for safety. This demonstrates memory protection. Without the kernel, a bug like this could corrupt the whole system. When an app wants to save a file or talk to the Wi-Fi chip, it can't touch hardware directly. It makes a system call like open or read, and the kernel handles the rest. Even a simple Python like this triggers the kernel to write to disk. When hardware needs attention, like a key press or incoming data from the network, it sends an interrupt. The kernel jumps in, pauses whatever was running, handles it, and resumes. It's like being tapped on the shoulder. The kernel is always listening. The kernel isn't just important, it's critical. If it fails, your entire system goes down. That's why you get the infamous blue screen of death on Windows, or a kernel panic on Linux and macOS. There is no backup plan, because the kernel is the plan. Back in 2018, the meltdown bug broke the trust. It let attackers peek into kernel's memory from regular apps, shaking the entire industry. And fixing it required patches to every major operating system worldwide. That's how big of a deal the kernel is. Many engineers obsess over the kernel because it sits at the crossroads of hardware, security, performance, and stability. Whether you're debugging a memory leak, optimizing I/O, or tuning thread scheduling, the kernel is involved. But not all kernels are built the same. The 2 major designs are monolithic kernels and microkernels. In monolithic kernel design, almost everything, memory management, file system, device drivers, runs inside the kernel space. That means it's fast because everything talks internally without extra hops. Linux and Windows, mostly monolithic. But if something crashes, like a buggy driver, it can take the whole system down. A microkernel does the opposite. It keeps only the bare minimum, like CPU scheduling and memory management inside the kernel. Everything else runs in the user space as separate services. It's slower but safer. If a file system crashes, you can restart just that service without rebooting the whole OS. Mac OS, for example, is based on Mac, a microkernel. Note that many real systems are somewhat in between. For example, Windows and Linux are monolithic but can load modules like plugin drivers dynamically. And Mac OS is built on XNU, which is also a hybrid, a microkernel based but runs many things in kernel space for performance. Basically, monolithic means faster, more efficient, whereas microkernel is more modular, safer in case of failures. And by now, you have probably seen the word kernel pop up in AI, GPUs, and even quantum computing. It's actually the same idea at its core, something that sits close to hardware and runs at high efficiency. In GPU programming like CUDA, a kernel is a small function that runs in parallel across thousands of GPU cores. It's called kernel because it's low-level, hardware-near routine, just like an OS kernel is. In AI workloads, these kernels process tensors, train models, and move data fast. In quantum computing, researchers are designing quantum kernels, the layer that manages how qubits execute instructions. I won't go too deep here, but if that sounds confusing, don't worry. I'll be doing a video soon on how quantum computers actually work and how they are starting to need operating systems too. The kernel may not have a UI or flashy animations, but it's doing the most important work, keeping your system running safe and fast. So the next time you boot up your computer or run your code, remember, there's a powerful piece of software at the heart of it all, the kernel. Hope this gives you a clear picture of what the kernel really is and why it matters. And if you enjoyed this breakdown, there's a lot more coming, including a full video on how quantum computing works under the hood. And guys, liking, sharing, and subscribing really helps me keep making videos like this. It tells the algorithm and me that you found it useful. Thanks for watching, and I'll catch you in the next one.